All right. Hello? Yeah, okay, great. Okay, so welcome to the third lecture of the Replica-Exchange Wang-Landau sampling. I want to specially mention about this. On Monday, David has already talked about Wang-Landau sampling. On Tuesday, I talked about the Replica-Exchange Wang-Landau algorithm and some scalings and how to measure the speed ups. And so today I will talk about how to really write a parallel program. So I will not talk about everything, of course, because this itself can be a semester-long course or more even. But what I will introduce to you is the message passing interface, and I hope, and I will have some demonstration codes to show you. Especially I want to mention about that Thomas Vogel was the first author of the Replica-Exchange Wang-Landau sampling paper. And so when, well, originally he wanted to come here to teach you about the Replica-Exchange Wang-Landau sampling technique himself, but he has classes to teach because school has already started in the US, so he cannot come here because of his teaching duties. So that's why he actually volunteered to help us with something. And then we were thinking about how to really do this mini course. And then I was thinking, there may be really a real programming session or some small codes to demonstrate how we implement the codes will be useful. So then Thomas volunteered to give his POS model code as a demonstration, and we will make all these codes open and online with the proceeding paper. So one bonus here, for those of you who really want to implement Replica-Exchange Wang-Landau sampling, ask questions, because if we cannot answer this here, we can answer this here, or if we have no time to answer it here, we can write this down in the proceeding paper. So if you can think about questions later on, please send us emails, and we can, as long as it's before the deadline of the proceeding papers, we will put the answer in the paper. Okay. Yes, yes. All right. Ooh. Is it? Yeah. Hello? Yes. It's working? Okay. All right. So the plan for today is as follows. We'll do a very quick recap, 2 minutes recap of Replica-Exchange Wang-Landau sampling. And then I will go into the message passing interface MPI. And then in between the explanation, I will show you some simple codes to do the programming. So it is not a full introduction of the MPI, but I hope the simple concepts highlighted here will help you learn MPI more if you're interested to do this later on. So Replica-Exchange Wang-Landau sampling. I will not repeat Wang-Landau sampling here because we have already heard about this several times this week. But for Replica-Exchange Wang-Landau, what is different is that you divide the entire energy range into smaller pieces, and these pieces have to overlap with each other so that you cover the entire energy range, and these overlapping will facilitate the replica exchange. And then, so when you do the simulation, you do Wang-Landau sampling within just the window itself. But then once in a while, you freeze the entire simulation and ask, now I want to see whether I want to do the configuration exchange between different windows. Then here you need to look at the probability, acceptance probability, and see whether I want to accept the change or not. The acceptance probability is written in this form, which is a combination of the density of states between the density of state of one window and the density of state of the neighboring window, and also the entries of the corresponding new and old configurations. Of course, if one of the configurations is out of range, then you cannot have any Replica-Exchange, and you just reject the move and continue. Okay, MPI. So what is this? Many people took this as a library, and actually it is not a library. It is actually a specification of a set of rules, how parallel programming and especially how message passing, message exchanges between the CPUs should be done. So this is actually a set of rules or a set of standards how message passing should be done. If, for example, some library developers would like to write programs to implement message passing. So this is a specification, and that is why over time there are different implementations out there right now in the market. So this is a distributed memory programming model. So what it means is that if you think of the workstation in your university, you have a few or a bunch of CPUs connected to each other through the interconnection network. So when you write a parallel program, you need to treat these memory attached to a single CPU separately. And when you write a program, you need to think about, you need to distribute the memory needed by your program to different CPU. So this is called a distributed memory programming model. And another programming model is a shared memory model, where every CPU is connected to the same memory pool. And this is done, for example, on your laptop. You have quad-core or multi-core CPUs connected to the same RAM. So that on your laptop, you can also do shared memory. It's a shared memory architecture. So the good thing is that actually when you program a parallel, when you write a parallel program, you don't need to worry about whether your computer is a distributed memory architecture or a shared memory architecture, because you can still use MPI, and MPI will take care of this for you under the hood. So that's why when you write a MPI code, actually you can do this on your laptop. You just do all these MPI calls, and then when it is okay on your laptop, it uses your different cores in your CPU to do the message exchange. And then when you put this, transfer this on your the workstation in your university, it will work the same. Only that your MPI rank might be different. So I will explain all these terms to you later. So there are different standards over time. Right now, people are already talking about MPI 4.0, but they are only on the discussion level. Is the most updated standard written down right now out there in the documentation is MPI 3.1. But one thing I would like to mention about is that the implementation actually cannot catch up with the standard. So what it means is that you have the standard already out there on the website. It specifies that which functions or which capabilities an MPI should take care of. But in fact, the implementation is maybe 10 years behind or even more. So usually a lot of implementation now, they are mature for MPI standard 2 or 2.2 or something. But then some of the MPI 3 specification is already available in some of these implementations, but not all of them are available. So this is something you will have to pay attention to different implementations and look at their website and say and see which MPI 3 capabilities are available for you to use. And this is, I think, in the coming few years, this will converge and it will move forward. So how to write a parallel program? The first thing is to start from a serial program. So here I have an example of a hello world for a C++ program. Very simple. You have a function name, and here this is the main program. And then you just want to print out a statement, hello world, and then you return. Here, if you're not familiar with C++ program, this is the number of command line arguments that you pass into the program, and then these are the command line arguments stored in an array. Yeah. So now let's see how to extend this and write the first Hello World MPI program. I just extend this so that I have a little bit of space. The first thing to do is to include the MPI library headers. So this header is basically a place to store all the names of the MPI functions. And then when you include this, then when you write your program, you can call the MPI functions. This is a must to do. And then you write 3 lines, basically, the lines that I highlighted in red. Here I just need some parameters to pass into these functional calls. That's why I have these here. The first one is my rank. I want to know if if I'm working with 10 other processors, what is my ID? It's like my class ID in a class of students. So this will be stored in this variable, my rank. And I also want to know what is the total number of students in the class. What is the total number of processors in the entire MPI program, or the entire MPI call that you have specified. So this is a numpros, stands for number of processors. The first thing you need to do is to start up MPI like this, called MPI init, and you pass the number of arguments and the number of command line arguments in words. Just pass that into this function as well. And basically, it takes over and initialize the program. One thing to note is that all the MPI library calls, they are prefixed by this uppercase MPI. So then when you search your program, you know all the MPI library calls will be starting from MPI, so you can do a very convenient call here. The second line here is a function that gives you the ID of the current processor. So I need to pass in another thing called MPI com world here, because when you think about MPI, you have a group of processors, and this group of processors is located in a communicator. And this communicator's name is called MPI com world. Basically, it specifies the entire world of communicators, the entire world of people who will talk to you. So this is MPI com world. And then the third line here gives you the total number of processes that is inside this communicator. So this is actually specified when you start the program, when you run the program. So it will be specified at runtime. So yeah, when I show the examples, you'll see this clearer why this is needed. And then, of course, we have our print statement. And then after you have done all the things you want to do, then you need to call MPI finalize to close down MPI, and then you return the program. No, so this is actually a number you specify. So you specify how many CPU you want to use. It will not serialize, but this is just a, if it's too large, then it will not let you run, of course. But this is not the program's problem. This is your workstation's queuing problem. They will return and say, I don't run your program because you request more things than I can give. So it's clearer when I show the first code. Okay, so let's do it. So now you have a Hello World, MPI Hello World code already. And I have, is it big enough? Can the people at the back? Okay, all right. So I have an MPI Hello World program here. Let's look into it. So this is just the same Hello World program I showed. We have the library called, and then initialization. I want to get my ID. I want to get how many number of processes are running, and then each process will print a statement saying hello to you, and then finalize MPI, and then we return. So now we run this program. Oh, no, wait. We need to compile the program first. So how to compile this? You use MPI-CXX. This command will be different if you grab the MPI implementations from different source. So well, before you can call this, of course, you need to install the MPI, the entire MPI package first. But this, if you want to know how to do this, you can come to me later after the lecture. I can show you on the computer. So it's very simple. If you have a Linux, you just go to the software manager, and then you can install that right away. So these commands will be different for different implementations. Some will use MPI CPP or something. So this you need to check which implementation you have installed. But the implementation I have installed is MPeach. So the way to compile a C++ program is MPI-CXX. And then I compile this program just like you have a normal program. It's done. And if you look at that, now I have an executable called a.out, just like before. And of course, if you are not aware of whether this is a serial program or an MPI program, you can always just run it. And it will treat it as I just request one core, and I just use one process in my MPI. So it will run like it will just run like a serial program. So back to your question, how do I know, or how do I specify how many MPI processes I use? Then there is another MPI command you can use, MPI run. Again, this is not the same for different implementations. So for different implementation, you might as well use MPI exec, standing for MPI execute. So you have these. I think it works, both will work for me, but I just stick to MPI run. Then I specify how many MPI ranks I want to call. Let's say I want to use 3 cores. I want to use 3 processes to run this program. Then you add this -n here, and then specify how many processes MPI ranks you would like to use. And here, if I use 3, and then the name of the program, then that means I use 3 MPI ranks to run this program and see what happens. So then you will see, you'll get a hello from process 0, you'll get a hello from process 2, and you'll get a hello from process 1. Hello, hello, hello. But you already see here from the example, they're actually not in order. So this is something you also need to keep in mind, that it is not a serial program. It will not execute the things for you from 0 and then 1 and then 2. The cores don't know, the CPU don't know whether, well, they don't execute based on what number you give them. They just execute all the things together, and when one of them is done, then they just print out the statement. So they might not be, well, of course, they might not be in sequence. And some of the time, if you run too many processes together, they will not be so neat to print out one line for you at a time. You might get some crazy output that hello from process and a hello from process, and then the sentence will be cut in different funny way. So this is something to bear in mind. The parallel I/O is a mess, and then you always need to take care of the I/O, the input-output here. All right, so this is the first hello world program, and now we already have said hello to the first MPI program. So this is just a repeat of what I have just said. You use MPI run or MPI exec, and then you need this -n flag to specify how many number of cores you want to use. Right. Okay. So another thing you already realized is that actually everybody prints a statement for you. So how is the program really executed on your workstation? It's like this. In our case, we have 3 processors, and each of them will be given a number from 0. It starts from 0, 0, 1, and 2. And each processor will actually execute the same program at the same time. But bear in mind that it is not only the first processor who sees everything, and then the rest is just sitting there. They actually see the programs at the same time, and then they run the program at the same time. And then that's why you see 3 different printouts from each of them. So this kind of programming model is called the single program multiple data model, because you have a single program and each CPU run the program at the same time, and they run the same thing actually, but then they handle different data. Okay, so next will be to learn about how to do the message exchange. So MPI gives you 2 very basic functional calls, and there are a whole lot of variants based on that. There are other flavors of doing this, but the simplest one is MPI send and MPI receive. They must be called in paired, because if I send something out, I need someone else to receive. So you always need to call these 2 functions as paired, but by different processors. An example is like this. CPU number 1 want to send this number to CPU number 2, and originally they have different initial numbers. Here is 10. So what you need to do in your program is that if I am CPU number 1, I call MPI send. I want to send this message out. And if I am CPU number 1, and then I want to receive this message, you call this, and then then CPU number 0 will know that I need to send this message to this guy, and this will actually overwrite what is originally in there for RAM number 1. Another function you can use is that what if I want to do the send and receive at the same time? So this is another example. If RAM number 0 has A equals 10 that wants to send to RAM number 1, and then RAM number 1 wants to send another message to RAM 0. And here the requirement is that these needs to be in separate space. So what will happen is that if both of them call MPI send receive, these will be sent to the other processor, and then these will be sent back to another processor. And here you see the values will be not exchanged, but you get one number from the other, and then you also receive another. You send one number, and then you receive another number. This is MPI send receive. Another thing which is more convenient and is used a lot in Replica-Exchange Wang-Landau is, what if I just want to exchange? I don't need 2 copies, but I just want to give you a 10 and then you give me back 20, which is good. So because it saves some memory. So here then you will call MPI send receive replace. So what happens here will be you just exchange the numbers, and then you get the other's number, and then you send this back to the other. Okay, so yeah, I have already talked about MPI com world. So this stands for the world communicator, or the initial communicator established by your MPI program. So if you realize that we haven't done anything, it is actually a communicator defined by MPI by default. So we don't have to do anything here to specify what is my neighbors to communicate with. This is already done when you do the MPI run minus n, the number of processes. It puts all these processes into this MPI com world. Of course, the functional calls are not as simple. You have to pass in a lot of arguments in the functional calls. So here I just give an example in MPI send and MPI receive, but the other functions I just talked about, they work in the same way. So once you understand all these parameters, then a lot of functional calls can be called in the same manner. So for an MPI send, of course, you need to specify what your message is. And then you need to specify how large your message is. For example, before we only exchange a number, so this count will be 1. But if you want to exchange an array, like an array with 10 elements, then here the count will be 10. And then you have to specify the data type. It is not just the data type that you specify in C++ or in Fortran. There is a one-to-one correspondence between the data type you use in C, C++, or Fortran to MPI data type. I will talk about this in the next slide. But it's basically specify what type of data you are transporting. In the previous example, it was an integer. So you have to write it down here. And then you have to specify, of course, who is receiving your message. And this is the ID of the receiver. There is a strange number here called a tag. So the tag here is basically you say, I'm now sending a mail to someone, and this mail will have like a label on it. And then you know that this is something that you let the receiver know that this is something you are expecting. So why is it important? Because sometimes you might want to send two messages to the same processors, to the same processor, but then these two messages are different. So it always happens. For example, you can think about you want to email a person, but you might email a person on two different subjects, right? So here, if you write an email, you specify a different subject lines, and then you send two emails. And this is the same here. The tag here basically specifies what kind of message I'm talking about here. So this tag is about deadline for the proceeding paper, but then another message I want to send maybe this is the deadline for submitting a paper. So here you have to specify, and the message could be the same. The message you send out may be just a date here, and then in another email is another date. So that's why it's important to have a tag here to specify which kind of message you're talking about here. And finally, you have to specify the communicator, because if you go deeper in MPI, you can actually group different processes into different communicators later on. And in different communicators, they might have the same ID. For example, if you think about a class of students, you want to send a message to a student who is in another class, then here you need to specify that I'm not talking about processor number 2 here in my class. I'm talking about processor number 2 in another class. So this is why you also need to specify the communicator here. But in our simple example, we only take MPI COM world because we have not split all the processes into different classes. It's the same for receive, but only that this time you need to specify from whom you are receiving the message to, and what is the status of the communication. So basically, whether you receive the message successfully or not, or the size of the message that I receive is also stored in this status here. All right, so MPI data type is very simple. Actually, there is a one-to-one correspondence. It's just that it uses that because for Fortran, I think, for example, char will be character, and then int will be integer. So, but there is a one-to-one correspondence here. I already talked about MPI COM and status. Yeah. So with these, let's look at another example. All right. Okay, yeah, great. So the entire program is just on one page. So this is exactly what we will do when we want to do a send or receive. Just one message passing. You do the same thing as in the Hello World code. You just initialize everything, get my own ID. And then, so you see here there is an if statement. And this is how to distinguish between sending a program or receiving a sending the message and receiving the message. Here I write in a way that ren number 0 would like to receive a message from ren number 1. And so if my ID, my rank is 0, then I call MPI receive. I want to receive a message. Oh, yeah, great, thank you. And then if I am rank number 1, then I get a message from rank 0. No, I send a message to rank 0. So it will call MPI send. And then the message I am sending here is just a number, it's an integer. If I am neither rank number 0 or rank number 1, then I just do nothing. I sit there. Right. So this is the this small program that does a message passing between RAN 0 and RAN 1. So again, you compile it using MPI 6, and then you run it with MPI run. Let's say I have 4 processes this time. Oops. Yeah. So then you see now RAN number 2 and RAN number 3 don't have anything to do. So they just sit there. RAN number 0 receive a message, number 10 from RAN number 1, and RAN number 1 just send a message to RAN 0. So this is how to send and receive a message. Okay, yeah, I will not show this now. It's just a little variant. All right, so far we are just talking about communications between 2 processes. And you can already do this actually collectively. And the send and receive, or send, receive, replace, we use a lot in Replica-Exchange Wang-Landau. And very rarely, but this is still very useful, is to have the basic, some collective communications. That means now you are not just talking to one processor. You are talking to all the processes in your communicator. So 3 very common functional calls are here. One is MPI broadcast. MPI broadcast is basically what I'm doing. I am talking, and I broadcast my message to all of you. So this is MPI broadcast. MPI scatter is a little bit different. It's like if you're a teacher, you distribute your graded exams back to your students. Every student gets a unique paper which contains the grades and then contains the marks. And this is MPI scatter. You are sending different messages to different processors. And then MPI barrier is basically a waiting point, because as you have seen, all the processes, they do things in a different pace, and at some point you want to make sure everyone has already get to this point, and then we continue to the next step. So here you will call MPI barrier. So far, okay? Okay, yeah, great. So the next will be to map all these MPI basic knowledge back to our programming. Back to, so here I do this example with Replica-Exchange Wang-Landau. So how to think about this? You already know that every processor would run the program at the same time, but they will execute this individually. So you start from a single serial Wang-Landau sampling, and then if you do nothing, if you just type a.out, then it will just execute as if this is a serial code. And then, of course, if you want to have more walkers, or you want to do Replica-Exchange Wang-Landau, the first thing is that you need to give different rank a different energy range. This is the first thing to do. So this is very easy to do, because you can do this with an if statement, or maybe you can even calculate this based on what ID you are. And occasionally we need to do Replica-Exchange, right? So what it means is actually that you need to have some communications between a certain selected set of processors. So this is what we need to do. And so think about what needs to be communicated in Replica-Exchange Wang-Landau. So for sure, we need to exchange the energy. Let's say you have the entire Replica-Exchange Wang-Landau program frozen, and you want to see whether you would like to do an exchange with another processor. So the first thing you need to know is, what is your energy? And I also tell you what is my energy. So this is the first thing you need to know. And then once you get the energy, then of course I can look up my dense of state table and say, okay, I have the dense of state here, and then for the new energy you're going to get or you might be getting, you have another dense of state. And then from this information, you can already compute whether you want to accept this exchange or not. And you can, of course, do this at the same time, but there is a tricky part here, because the random number generator might not be the same for different processors. So here you also need to synchronize. And there are two ways of doing this. One is that only one of the pairs, one processor of the pairs does the calculation, and then I send the decision back to you. And the other way I do more in my massively parallel Replica-Exchange is that at the very beginning, I synchronize the random number generator. So there are different ways to do this here, but if we are only running a small program, basically you don't need to synchronize the random number generator. You just send back the decision. It's not too time consuming. And at the end, of course, if you would like to exchange the replica, then you need to exchange the configuration with the partner. So if you put this in our Wang-Landau sampling, as I said, we always start from the serial program. So here I don't have a program, of course, but you can think about this is a serial Wang-Landau procedure. So and then now we know if we want to do Replica-Exchange Wang-Landau, we need these four things, four messages to be exchanged. And you just need to put this in the corresponding or in the correct place in our serial program. So if you think about that, where should we put A, B, C, and D? The answer is here. So here, when we generate a trial configuration, we calculate the energy E. You still do this individually, separately. But then afterwards, once you have the energy, then you exchange this with your partner. And then you also look up the dense of state, your own dense of state, and the partner also look up its density of state, and then now we can exchange. Why is that? Because in the acceptance probability, we need all these four data to compute the acceptance probability. So that's why there is another exchange here. The dense of state also need to be exchanged after you receive the energy. So here you can already think about you need to make sure that the energy is received before you compute the dense of state, and then you exchange the dense of state again. So with these, then one of the processes will calculate the whether to accept this or not, and then you need to send the decision back to the partner. And then if you decided to have a Replica-Exchange, then you exchange the configurations. So all these are actually done in step number 2 and 3. Here once you have calculated the energy, and then once you have calculated the acceptance probability. So at the end of the simulation, you can also imagine that some processes will finish the Wang-Landau sampling earlier, and then some processes will finish the Wang-Landau sampling later. So at the end, you also, from time to time, need to communicate to all the processes and say whether I have completed my task or not. So that's why here, it's not very often, but from time to time, you still need to talk to the rest of the processors. Yeah, so that's it. So for the last few minutes, I just want to show, I will not show you a lot of the codes, but I just want to show, yeah, yes. There's no difference. There's no difference. Let's see. We have 18,000 nodes, and yeah, 18,000. Yeah. In the program, you cannot. But usually what you can do is in your submission script. You see when you submit a program to a workstation, usually you have a submission script. And that submission script, you specify how many core I want and what ranks or really physically what partition you want. Yeah, yeah. Right, yeah. So another way is actually MPI, let's see, MPI run. Yeah, thank you. This is very important. If you do an MPI run help. Yeah, so if you're not sure what flag you use, you can use MPI run dash dash and then help. And then it gives you all the options you can use. And depending on the MPI implementations, you actually can specify which rank you want to map to a physical thread in the physical computer. So this is done on this line, actually. Usually our MPI run line can be super long if you really want your program to run fast and to map to the actual topology of the computer. So this is, yeah, this is done actually in the submission script. All right, so the last thing I would like to show you is this code will be available in on GitHub, or yeah, we will find a place to put it as soon as we have these proceedings. We will have the link there to this code. So let's see, you compile this code, which is actually a Replica-Exchange Wang-Landau code. And then you want to run it. The thing is that I always forget what command line options I would like to pass. So if you just run it, then it will remind you what you need to do in the command line. So actually, what I want to do is I want to do a MPI run with 3 windows, 3 smaller windows. Then I specify this on the on this line here. I want 3 processes, and the code is written in a way that 3 processes means that you want to chop the entire energy range into 3 windows. And then my code, of course. And then you specify how much overlaps you want between the windows. So usually 0.5 is okay, and if you want to have smaller or larger overlap, you can adjust this here. It's between 0 and 1. And then one feature I have talked about actually in the Tuesday tutorial is that we can we can have some, we have multiple walkers in the same, with the same energy range, and this is what is specified in here. Then in this case, I just want one walker to take care of one energy range. And then you can specify how many Monte Carlo steps you want to do the Replica-Exchange. So for example, 10 is good, or a small number is good, but not too small. So 10 Monte Carlo steps to 100 Monte Carlo steps is suitable. And then finally, the random number seed, just a random number. So then you can run the code. Sick thought. Yeah, okay, this is the danger. This is the danger of running a program online. Let's see. Oh, but it finished. Interesting. Well, anyway, so I will fix the program for sure. But yeah, but so what you will see is that there are a lot of outputs in between, and these are the histograms. Interestingly, it's finished. And these, for example, is where the final tensor of states are. So if you look into one of these, oops, yeah. So these are the. We will document this in the proceeding paper, but this is basically the energy. And then this column is the tensor of state, and then this column is the final histogram. So, and we have 3 pieces. You see, we have 3 pieces here because we said we want to have 3 CPUs doing 3 different windows. Right. So this is what I want to show you. Last word is this. I learned MPI all by myself, and I found all these references very useful. So there is a very nice MPI tutorial written by Lawrence Livermore National Lab, and surprisingly, the MPI standard documentation is super nice, super easy to read, and it's free online. So if you go to this website, you can download the documentation. It has a lot of example codes in the documentation, and you can just follow it. And basically, you can have all the example codes actually in the documentation. And finally, this book is very nice if you want to learn about more the background information about parallel programming and how to do this with MPI. Right, so I think I run out of time. Questions?